Having laid the foundations for the nuclear shell model in the previous lecture, we will look at some of the important features um, and the results of the nuclear shell model. Experimentally, what is observed is that if the number of neutrons or protons are equal to these numbers, they are much more stable. These are known as magic numbered nucleus. So these magic numbers exist both for neutrons and for protons. So how do you rationalize this feature is one of the important motivation for nuclear shell model. And in this feature, nuclear shell model does much better than the liquid drop model. So the model result should be able to explain this. We will see that in this lecture. So these magic clusters will evolve, will just come out from the ladders of energy levels that are presented. So this cannot be accommodated. That is, the correct experimental observation cannot be accommodated without appealing to what is called the spin orbit coupling. These are all fairly quantum chemical concepts or topics that you might have seen in an atomic physics class. So I would encourage you to take such classes if you want to understand these in detail, but the broad features can be understood without detailed quantum mechanics. What exactly do we mean? Because the orbital angular momentum is similar to the spin angular momentum. In what way? They're both angular momentum and they are both vectors. So they can add and subtract each other. So there are some vector coupling rules for coupling the spin angular momentum with the orbital angular momentum. So when this is coupling is strong, uh, the there is a different quantum number that becomes important. J is obtained from the L and S, where L refers to the orbital quantum number, S refers to the spin quantum number. L is a product, is something that you get by adding or subtracting these two angular momentums via certain rules. We won't go into this in detail. So it is important to understand when this coupling is strong, L and S are not good quantum numbers because they are not individually conserved, right? When we say quantum numbers, it is a scalar that specifies a conserved quantity. That's what we mean by a good quantum number. Okay. So, but overall, J is conserved quantity. That is, J is obtained via uh, L and S in some manner. Okay. So, but however, you in when the coupling is strong, instead of using L and S, there is another quantum number which specifies a conserved quantity, the total angular momentum that is obtained by vector coupling from L and S. This J is a good quantum number. If all these things appear like jargons, you have to improve your quantum knowledge, but it is not too important for the scope of this class. What is important is to understand this structure. So, why is this important? In your high school, you had seen something like the Aufbau's building up principle, right? What does that? It provided you with a ladder of energy levels, which was utilized for filling up the electrons of different atoms in the periodic table. So this is the equivalent of Aufbau building up principle. So here we are looking at building up the nucleons within the nucleus. So with a lot of information present, we will go through this slowly. Okay. So this specifies the n quantum number, right? We have introduced the n quantum number in the previous lecture. So n equal to 1, n equal to 0, n equal to 1, n equal to 2, n equal to 3, and so on. For a specific capital N, okay, so all these things indicate the capital N, and we are quantizing within a harmonic oscillator potential in 3 dimensions, right? So we have shown that potential also in the previous lecture. So this specifies a capital N. For each capital N, we had specified what can be the L and small n quantum number, right? So within that constraint, that is capital N is equal to 2 times n minus 1 plus L was a specification. Within that constraint, if n equal to capital N equal to 0, you can have only 1s level. If capital N is equal to 1, you can have a small n equal to 1 and L equal to 1. Here L equal to 0, right? So within that formula, that is capital N is equal to 2 times n minus 1 plus L, we can get these levels, okay? So within these levels, so when you have specified this, you have specified the L quantum number, and each nucleon, that is proton and neutron, are fermions. So the spin quantum number is also known. And you have this coupling between L and S, from where you get J, right? J is obtained in 2 ways, right? When L equal to 0, when S is equal to 0, I mean, when for S orbital, you have L equal to 0. And S quantum number is half, right? So you can have only, J can only be half. So here, L quantum number is 1, S quantum number is half. So you can either have 1 plus half, that is J is equal to 3 by 2, or you can have L minus S, so 1 minus half, so J can be half. So L plus S and L minus S gives you 2 different levels, and we have looked at the occupancy in earlier class, earlier lecture, what is the occupancy possible. So likewise here, when you have let's say d orbital, for d orbital, L is equal to 2, so you can have L plus S, that is 2 plus half. J can be 5 by 2, and when you have 2 minus half, that is L minus S, you can have J as 3 by 2. So likewise, you have also obtained the J here, so it is similar to J here, and so on, right? So for different L quantum number, you get L minus S or L plus S. So here L corresponds to 3, so L plus S corresponds to 7 by 2, L minus S corresponds to 5 by 2. So here, this is small n, this is L quantum number, this is the J quantum number. So we know how to calculate the occupancy from previous lectures. We have given the formula, but what is important? We said that this structure, how did you get this structure? Via quantum mechanics with some reasonable confining potentials, you were able to get this structure. And what is important is the following. When n changes, that is n equal to 0 to capital N equal to 1, or capital N is equal to 1, or to capital N equal to 2, there is a jump in energy. So this level is much lower than the next level, all right? This level is much lower than this level. This level is much lower than this level, and so on, right? So this level is much lower than this level. Okay, so again, this where see here, this comes from just specifying n, right? So here, unless you take the coupling between L and S to give L plus S equal to J equal to 4.5, you cannot rationalize certain feature. What is the feature we are after? We are after Y are certain numbers called the magic clusters stable. So experimentally, it was observed that if you have 2 neutrons or 8 neutrons or 20 neutrons, 28 neutrons, 50 neutrons, the nucleus is stable. Likewise, if you have 2 protons, 8 protons, 20 protons, 28 and 50 protons, the nucleus is stable. In the motivation for the nuclear shell model, we had talked about isotones for capital N equal to 50, right? So that is where this observation is. So within this principle, that is within this nucleon building up principle, we are able to rationalize why certain levels are much more stable to the next higher level. So there's something like the noble gas configuration, right? So you have, when you say magic cluster, you are talking about certain closed fill shells, which are much more stable than the next highest level. So that is brought out from the nuclear shell model along with L coupling between L and S to give the J quantum number, right? So all these things have to be brought together to explain this. Not only this, you can also go to higher levels and again to get the magic clusters right, you have to incorporate the coupling between L and S to get the J quantum number, right? So you get all these things. So this is the central result. Okay, so again, I'm stressing that a detailed understanding of quantum mechanics is not important for this class, but these models have been obtained by solving the quantum mechanics for nucleon structure within a reasonable confining potential. Okay, so quantum mechanics is quite important to get this, but what we are going to be using are the results of quantum mechanics as applied to nucleons. So the important consequences, we are able to get the magic numbers, which was the main deficiency of the liquid drop model. Okay, so this is a great success of the nuclear shell model. So let us contrast. Okay, so this nuclear shell model is applicable both to protons and neutrons. So once you have these levels, we can use these levels to fill the neutrons. Supposing you fill your nucleus has only, let's say, 2 neutrons, you fill here. If you have 6 neutrons, you fill till this level and so on. Okay, so this is the building up principle for nucleons. Try to understand this in the context of the way you thought through Aufbau building principle. So once you have a ladder of energies available to you, you can start filling up the nucleons, either the neutron or the protons. So we have already mentioned that the shell structure is relatively insensitive to nature of the confining potential. This is a big, you're lucky to have this insensitivity because the exact, the detailed nature of the strong interactions is still not yet known. But despite that ignorance, with reasonable confining potential, you are able to get the general features of energy levels or within the nucleus. So both, once you have these energy levels, both protons and neutrons can be accommodated within the ladder of energy levels available to you. The depth of potential for protons is lesser because of Coulomb repulsion. The neutrons do not feel Coulomb repulsion. Therefore, the depth of proton potential felt by the proton is lesser. So it's the proton potential is less deeper compared to the confining potential for neutrons. So again, so we contrasted. These are similarities between protons and neutrons, filling up protons and neutrons. There is some dissimilarity in the absolute value of energy levels for protons and neutrons because of importance of Coulomb interactions for protons. Let's also contrast and try to see similarities between electrons, protons, and neutrons. So when you had looked at the half-wave building up principle in your high school, you would have used this rule, Hund's rule for maximum spin multiplicity, right? So this can be derived from, of course, quantum mechanics, but you would have used this rule, right? When you have, let's say, electronic configuration for nitrogen, okay? So how do you put in the valence electrons in the p orbitals? Okay, so you would have seen there were three p orbitals. Either you could have specified that as px, py, pz, or p plus 1 minus 1 0, which wherein we specified the L quantum number and m sub L quantum number. Anyway, the main point is you would have used this spin multiplicity rule. You want to maximize the spin multiplicity. However, this rule is not there for building up the nucleon structure because pairing interactions is much stronger for nucleons. Okay, so without obeying this model, without obeying this rule, we are going to be always pairing the nucleons instead of multiplying the maximizing the spin multiplicity. So building a principle for the nucleon prioritizes pairing. Therefore, this rule is not obeyed for nucleons, but it is obeyed for electrons. So once you have this ladder of energy levels, you pair the neutrons with neutrons, proton with protons, and start filling up the energy levels. So there is also one another feature of nuclear isomerism. So because of this coupling between L and S, the J states, okay, so are widely separated. Okay, the separation increases as you go to higher and higher N. So they are so separated that one of the J state is very low in energy. The other J state is very high in energy. Okay. So there are bunching of levels as you go towards the edge of these levels, and there is a gap. Again, there is a bunch of levels and there is a gap. So what the consequence of this is that there can be isomers. Okay, so the nucleons can be present in one of the levels, and to get de-excited, it takes some time to get de-excited to lower levels. Okay, so the nuclear isomers can also be rationalized within the nuclear shell model, which includes the coupling between L and S. So you can have metastable states of certain atoms. Okay, so typically these metastable states were arrived at via, let's say, some decay process. So M indicates the metastable process. Why do we call it metastable and unstable? Because these metastable states are can be isolated. Like, so you should know the differences. Supposing you in chemistry, we use reactants and product, that is clear. Then there are also reaction intermediates and transition states, right? reaction intermediates are local minima. So these metastable states are local minima. Like reaction intermediates, these metastable states can be isolated because they have some finite lifetime and half-life and so on. Okay, so to explain the nuclear isomers, the nuclear shell model with the coupling between L and S is very important. And these nuclear isomers can also be rationalized. And there are something called selection rules which govern these de-excitation to lower levels. We won't go into that, but all these things are part of a typical course in quantum chemistry or atomic physics. So please take such classes if you want to understand these features in greater detail. So in the next lecture, we will see few other properties related to nuclear moments and electric quadrupole moments. Those topics will be taught in the next lecture. Thank you.